Yeah, hello and welcome everybody. Thank you very much, Claudia, for the introduction. I'm very excited to be here today because, as you already said, privacy preserving machine learning is a topic that I'm really excited about. As Claudia has already nearly said everything about me, we can basically skip this next slide, but it's just about if you want to get in touch with me after the lecture today, you can do so over LinkedIn, Twitter, or write me an email also with follow-up question. Any kind of interaction is always appreciated in these times. So let's have a look. What are we going to expect in the next hour here? Basically, it's going to be an overview on the topics that are relevant if you want to bring privacy together with machine learning. But why is it important at the first place? Maybe let's have a step back and take a look on a really interesting example on what happens if we don't think about privacy in any use case. I will start this example maybe with a little trivial question. Who of you knows Netflix? And who of you watches your films and series there? Well, unfortunately, in this setting, I can't see your faces, but I will just imagine some of you right now nodding their heads and saying, yes, we do. And of course, as an informed user, you will also probably know that Netflix collects a lot about data about you. So they collect what you watch, when you watch it, when you pause, how long you pause, what scenes you rewatch, etc. And this might reveal quite a lot about you as a person and your preferences already. But we will see that it needs actually much less data to identify you in the whole mass of Netflix users. So let's see, why is Netflix collecting this data in the first place? It's an easy answer. They want to produce and show you content that you like and that makes you stay on their platform. And therefore they need to know what you like. And they are basically doing that with a recommendation algorithm that just filters somehow what is going to be relevant for you. And improving this recommendation algorithm helps improving their quality. So it's definitely a key part. And in the past, Netflix has even made an event out of this improvement of the recommendation system called the Netflix competitions. That was for researchers and data passionates in order to participate in making the algorithm better. And the competition was started in the year 2006. It was about creating the best collaborative filtering algorithm to predict user ratings for films based on previous ratings by these users and no additional information about the user or the films. And the team that would achieve the largest improvement on the Netflix recommender would be awarded $1 million US. So given a data set that consisted of 4 items only, a user ID, a movie ID, a grade, and a date, the question would be who achieves to have the best recommender system. And Netflix provided around 100 million of such rows that we can see here. Each user was anonymized, so to say in quotation marks, by assigning an anonymous ID. Each movie also had such an anonymous integer ID, and then you had the grade that the user gave to the movie and the date when the user gave this rating. And for the evaluation of the quality of the final recommendation systems, Netflix also had an apart data sets where the grades by the users were only known to the jury. And at the end, when the participants would hand their recommendation system in, the jury would say which one is doing best on this unknown data, and they would award the prize accordingly. The competition went on for some years until 2009, but in 2010, Netflix was sued because of privacy concerns. So what happened in between? In 2008, some researchers managed actually to de-anonymize this dataset. So they found back a mapping from the user IDs, the anonymous IDs, and the anonymous movie IDs back to the real names and real movie names. How have they been able to do so, given that Netflix, in quotation mark, anonymized this data? Well, the researchers used the so-called linkage attack. And this linkage attack should link some knowledge about the anonymized data on the one hand with some background knowledge on the other hand. Formally spoken, a linkage attack takes place when someone uses indirect identifiers such as a postal code, a birth year, or even the day when you watch a movie that taken alone just would not reveal any individual. But if you take them together, they might be sufficient to re-identify individuals in an anonymized dataset just by matching them with this other dataset. So where did the background knowledge in the Netflix example come from? The researchers just took the Internet Movie Database, which is a database that has a large number of personal movie ratings. But in this database, users can submit their ratings with a real movie name and their real name. And of course, for Netflix users who are also using IMDb, it's expected that there's a strong correlation between the private Netflix rating and their public IMDb ratings. Yes, it's true that the users will not rate every movie on both platforms, maybe, but the researchers found that it was even with a handful of movies possible to de-anonymize the data set. And what they basically had here was the second data table where the names were in clear text and the movies were also in clear text. And then they looked what attribute pairs were the same. And when they were the same, they just matched it up. And with only 8 movie ratings per person, they were able to re-identify 99% of the records in the Netflix dataset. If you want to read more about what they did or how they did it exactly, I posted you the name of the paper here down on the slides. It's a really interesting read. But of course, what you can just see directly is that what happened here is a real privacy breach. And this attack basically made people aware of the fact that when you publish data, you must be extremely careful. And in the course of today's lecture, I will show you that the same care needs to be taken when, for example, releasing machine learning models or when you provide access to them. So before we are going to have a concrete look in these machine learning attacks, we will need some background such that we use the same terminology in the following. Afterwards, I can speak about the privacy attacks against machine learning and how to prevent those attacks. At the end of when talking about all the different prevention mechanisms, we will focus on differential privacy because this is the topic that I am mostly dealing with in my research. So this is the point where I know most about and can share most with you. So let's start with talking about what privacy actually means. The topic of privacy is actually closely related to the topic of security. Maybe you might have already heard about the 3 security goals of the SIA goals. So it's confidentiality, protecting data from unauthorized access or views, availability, making sure that the data is accessible, and integrity. So basically protecting the data from any change. And you might already notice this confidentiality sounds quite a lot like privacy. So you don't want your data somehow accessed by someone unauthorized or just without you controlling it. But the term privacy, however, can be seen in different, I have seen it in different definitions, sometimes on the same level exactly with this confidentiality, but sometimes also on the same level as security. And my impression to this ambiguity is that it results from the fact that the term privacy is usually employed to refer to 2 different things, namely data security and data protection. And in data security, it's indeed about the protection of your private databases, systems, machine learning models against the unwanted, unauthorized access. So here it's basically really similar to confidentiality. And the focus here is more on a technical and procedural treatment on the data. So we keep our data private by encrypting it, or if we have it on a hard disk by locking the hard disk in the safe, or choose what you like. And in data protection, on the other hand, it's about the processing of personal data, namely whether this data is processed lawfully, how it's obtained, how it's processed, updated, or deleted. So it specifies how people should deal with this data. And this, for example, is also specified in a data protection law, such as the GDPR. Therefore, data protection is more about a legal issue with fewer emphasis on the technical side. And if we consider it as such, it's also valid to put privacy on the same level as security somehow. And once you dive into privacy, you will meet two topics a lot. The first one being information leakage. And an information leakage is basically about you have a closed system and some data flows out of it without you wanting it. But that does not necessarily need to be personal data, but it can also be some weather data in the system or some sensor data in a production process. So this information leakage can basically be prevented already with the technical measures, for example, of the SIA goals. But then on the other hand, you have also privacy leakage, which means that personal data is leaked from a system. And in order to prevent that, of course, the necessary condition is to keep the data secure, but you also need to look on the sufficient condition, namely data protection. Now that we have a vague idea maybe of the terms of privacy, let's jump into the next part of privacy preserving machine learning, which would be machine learning. And I guess that some of you might have already some ideas from university courses. For those who don't, it's not really important. I try to give you a little overview so that you will be able to follow the rest of the lecture. And in machine learning, what you basically have as a start is some data. In the Netflix example, we started out with the data of a user, movie, date, and the ranking. And today we will just focus on that kind of classifiers where you classify some of a ranking. Otherwise, we will exceed the scope of the lecture. And in classifiers, you have this one part of the data, which consists of properties, and the other part, which is a label. So here our properties in the Netflix example could be, for example, the user, the movie, and the date. And based on those information, you want to predict the class of the label. So it's 1, 2, 3, 4, or 5. And basically with your classifier, you want to predict unknown data. So when a new movie is released, just by looking at the previous recording through your model, the model will be able to predict with a certain probability how a user would rate this movie. And how do we obtain this knowledge in a model? I try to visualize the process here a bit for you. And the first thing that we need to do is to split the data set into 3 different sets, a larger one and 2 smaller ones. And the large one is the training set, where we learn the properties from. One of the smaller data sets is the validation set, the set that we use in order to tune the performance of our models. And the third one is the test set, on which we evaluate the performance of our final model. And then imagine at the beginning, we have a model that knows nothing about our data. So it's basically just something that has random parameters. But then we provide our data as input to the model, and the model processes it somehow. And this processing, you can basically imagine that as some matrix multiplication. So you have the model that consists of large matrices of numbers, random numbers at the beginning. And by forwarding or processing your image data or your movie data through the network, then you will end up with a class prediction of this model. And when you have the predicted class of your model, you can compare it with the original label that you have, and you can see how close they are together. And this difference between the original label and the predicted label by the model is usually considered the loss. And our goal in machine learning is to minimize this loss such that the labels predicted by our model come really, really close to the original label. And what we then do is we evaluate sometimes putting the training data into the model and then looking at the labels. And then we need to adapt something. But of course, we cannot adapt the data. We can also not adapt the labels. The only thing that we can adapt is basically these parameters in the model. So we will play around with the parameters and change them slightly such that our labels always become closer to the original labels. And by doing this process of comparing the loss, changing labels, predicting again, changing labels, then we will end up with a model that finally knows something about our data. And then when we finally apply it on the test data, we can evaluate how good the model is on completely unseen data by comparing the loss again. So how are the predicted labels in comparison to the original labels that we have for the test data? And now, before we look into how we could attack those systems, it's really useful to first get an overview on what in those systems can be attacked and to understand what an attacker can do, can know, and does want to do. And let's first about the knowledge. In the Netflix example, for example, the researchers had a lot of knowledge because they had the whole data set that they were given by Netflix, and they had a huge amount of background knowledge. And in machine learning, it's also possible to run attacks with full knowledge, and we call these attacks white box attacks. In the white box attacks, you have a trusted environment in which you hold your training data, and this environment is basically closed for everyone. But then you train a machine learning model, and the model resides outside this trusted environment, such that the public and also thereby potential attackers can access the model, find out the parameters, the type of model, and can just interact with it and to learn about it. And on the other hand, on the other scale, we might have the black box model, where you have your data in the trusted environment again, but also the model together with the data here with no access from the outside, apart from a very specified API, so an application programming interface that lets the user interact with the model. And of course, like always in life, there's not only black and white, but there are like 100 shades of gray in between, where you have knowledge of data attributes in the attacker, of the data distribution of a model type, or of some hyperparameters of the model. And based on this knowledge, attacks can be stronger or less strong, of course. Then what can the attacker do? In the Netflix example, basically the researchers could interact with their data set unlimitedly. So they were given the data set and then they could just use it and reuse it tons of time. And in machine learning, this might be exactly the same, that you have an attacker that can query the model an unlimited amount of time and so get all the information out. You might, however, also encounter a setting where the number of queries is limited. So the attacker cannot interact with the model all the time, but needs to be quite focused in the queries. Then it's the question, what can the attacker actually ask to the model? Will the queries be checked somehow, or can he just ask everything to the model? And then there's also the other question in machine learning that is a bit even more interested than in data samples that are released. But the question is, can the attacker also participate in the machine learning model's training? On the first look, this might seem really absurd to you, because how would a stranger participate in the training of a model? But now think of, for example, what you do with your phone. You type there a lot, you go online shopping, and of course, all the data that you produce there all the time is propagated back to the company where they learn their models on your data. So you're basically participating in model training every day. So it's a valid scenario to assume that your attacker also here can contribute some data for your machine learning model. Gets a bit less likely when it's about removing training data from a data set or modifying training data, but there could also be scenarios, and these will define how the attack space is set up. And additionally, the last step on the scale is the question, what does the attacker actually want to achieve? So does the attacker or does he want to disclose the group or class privacy? And by looking at specific groups, so running a targeted attack, or is it just about any group or class that we have in our data set, which will be an untargeted attack? Or is it maybe about disclosing the privacy of some individuals? Then an attacker would also, again, have the question, do we look at specific individuals, or do we just look at the whole group of them? In the Netflix example, for example, we can see that there was an attack on individual privacy, because for individual users, they found out about the movie preferences, but it was an untargeted attack where basically all the individuals of the database were targeted. Then it's also the question, maybe sometimes we cannot find out anything about specific users directly, but we could at least identify some attributes for users. And apart from these, I call them technical goals, there are also the so-called underlying goals. So what does the attacker actually want to achieve? Does he want to, or does she want to harm the group of specific individuals or the model owner by stealing the model, for example, extracting the training data? Do they just want to have a bad publicity for the company? So maybe like the researchers for the Netflix case. Or does someone want to steal the model in order to build the model themselves that has even a better performance? So all of this is possible. And now that we know all these goals, we can definitely look into how concrete attacks are used to achieve those different goals. And I mean, for a long time, nobody was aware even of the question of privacy in machine learning, and applications started to emerge first in academia and then very quickly in industry, in companies, but then also in sensitive areas like medicine. And I guess especially for neural networks, there must have been this thinking, the model is a black box anyways, we don't understand if we put something in, why does something else fall out? So there shouldn't be any concern with privacy. However, in recent years, it was found that even though the functionality of something, of the model, for example, is not fully understood, and the model is a black box to us, the process of turning this training data into the model, so making it reflect by the model's parameter, does not correspond to anonymization or pseudonymization, and it is indeed partly reversible. We'll look at 4 attacks that use this partly reversibility of the model, and where we start with training data, have a model, and then we could do something that's called model inversion. We could do something that's called membership inference, something that's called attribute inference, something that's called model extraction. And we'll see how those different attacks work in a second. And we start with model inversion. And the model inversion, basically the goal is that you have given a model and you want to restore training data points or training classes from that model. Currently, if you have this trained model, it's not yet really possible with the attacks to restore data of individuals, so to have an exact representation of one data point. But it's possible to have representation of groups, namely of the classes that the model has been trained on. So in model inversion, the security goal is to disclose group privacy. Can be targeted or untargeted, both are possible. But what the model inversion returns us is just a representation of the average training data distribution for the model. And in order to give you a little impression how this would look like, I took the MNIST data set. This is just a very famous training set that you often use in machine learning, and it consists of images of the digits from 0 to 9, and you have around 6,000 images per class of these data, and then you want to learn the label. So if you give them like a little image of a 5, your model should say it's a 5. And I trained this model very shortly, and then I run a model inversion attack and ask the model to tell me exactly how his class 0 to 9 would look like. And this is basically what I got. So these are the average representation that a model learned from the classes that it studied. And in my opinion, those are quite good representations of the data that the model saw. So at least some data points look really like they would do in the original training data set. So if we have some specific groups or classes and we can find how they would look like, this can be, in any case, considered a privacy breach for those groups. Then we have the attack called attribute inference. And an attribute inference is mainly about predicting specific sensitive attributes of an individual in a data set. So for example, given that you have all your information, you have a user and you have a date of their review and you have a 1-star review. So you know that the user really hated one movie, but you don't know which movie it was. That was a secret. But then you can run an attribute inference in order to find out what movie the user really hated. And how you can do this relies basically on the assumption the model has been learned on this training data point, the user ID, the date, and the movie, of course, and it has learned that this combination leads to a 1-star rating. So the idea behind the attack is now that if you provide the correct tuple, so if you insert the correct movie ID, the confidence of the model will be highest because this is the point that the model has seen before. So the model will remember, this is the correct tuple. So all you need to do is to brute force over all possible movies. You will start with a movie, which is none, and the probability, and then for all the values in all possible movies. So you iterate over all the movies. You have the model predict, and you remember the confidence. And every time your confidence overpasses the previous confidence, you save this new value for confidence, and you save the movie as a movie. And this is just a really simple brute force attack that by the end lets you end up with the movie that led to the highest confidence of the model. So which might be the point where the model remembers having seen something and which might be the secret movie. So basically thereby the secret movie is revealed. Another really interesting attack is the so-called membership inference attack. And the main goal is basically, given any data point, determine whether or not this point was used for the training of the neural network. And I think that all of you will agree that this is obviously an information leakage, but I would like to show you how this can be a privacy leakage as well. So imagine you have a classifier that is used to classify user ratings only on adult movies. So obviously it needs to be trained on users who have watched this kind of movies. Therefore, if you find out that a specific individual is in this data set, then you have learned something about this individual, and this is obviously a privacy breach. So here we have a targeted attack that basically tries to disclose the privacy of a specific individual by asking, is this individual in the data set or not? And thereby you also learn some interesting attribute maybe about this individual. And how does such an attack work? Well, basically we start with our own model and a data point for which we want to know, is that model trained on this point or not? What we will do in the background is to train so-called shadow models. we do that by finding data that looks similar like the data that we have trained our own model with. But here, now we take these data points and we train a lot of models on them, where sometimes some data points are included and sometimes they are not included. So we train the models to be similar to ours, but here in this case, we know, has a specific data point been included in the model or has it not been included? And with this knowledge, we can basically train a binary classifier that when we give it a training data point and the output of the shadow model in this point, then the model, the binary model, can learn was the training data point inside the shadow model or not. And so we create a binary classifier that, given any model and any data point, learns to predict that or whether or not the point was included for training. And once we have this binary classifier, we can apply it just on our model and the data point that we have, and we will know whether this particular data point was used for the model training or not. The last attack that I'm going to talk about is the so-called model extraction. And here it's about that you're given a model, you either want to steal its functionality, so learn the task that the model has learned, which is, for example, in the MNIST data set, given a little number, tell me what number it is, or you want to replicate the entire model behavior, which would also include if the model learns something wrong. So if it's given a particular 6 and it says it's a 3, we still want to copy this behavior. And first of all, this attack might not be so clearly related to privacy. However, if you think of it, many of these attacks that we have seen now, we have seen that an attack in a white box setting is actually with a lot of parameter access, so where the attacker can do a lot more. So imagine you have given a model that is behind an API in a black box setting, but you know that your attacks will be stronger once that you have this model in hand. So what will you do? Of course, you will steal the model from this API, and then you have it in a white box setting, and you can do all your privacy attacks as much as you want, as long as you want, with unlimited access. So it basically gives you an advantage on knowledge and capacity. And how that works usually is really easy. You have a model, so our model behind the API. You take some data points by the best of the same distribution as the original model. You ask the model, what's the label for this data point? So the model acts as an oracle for you. The model gives you the label, then you have data points and labels. You use them to train a model, and basically you have the copy of our model that is pretty similar. And from here, now you can start using your attacks. I think it's pretty devastating, the ones that you've seen, what kind of attacks are possible against your machine learning models. But luckily, and this is what the second half of this lecture is going to be about, there are ways to protect your models. So the question then is, in what scenario or when, how could we apply privacy preservation for our machine learning models? And basically, if someone asks me this question, how will I include privacy for my machine model training, I have to tell them it depends. And it depends on a lot of factors, actually, because every different setting that you might be operating in requires different functionalities. But let me give you a quick overview on what kind of questions I'm usually asking to people when they ask me how to protect their models. And the first question I'm always asking is, how many parties involved are in the training process? So is it just you, your team, or will also another organization or another team have access to your data? Then where should the training and prediction take place? Are we talking about a centralized system where you collect all your user data, and then the infrastructure is your own, all the people working with the model, you know them, you are sure and secure that the data is really secure with you? Or is it the case that you don't have all the computational resources, for example, at hand, so you need to rent servers elsewhere, for example, with Amazon Web Services? So will you need to shift the training data somewhere? Or are you cooperating with another company and you want to train them jointly, and maybe you need to shift them to the other company to have it trained? So this is an important question. Then the next question is, who will be allowed to see and access the data? So is it again just one of your data engineers, or do you also need to give access to someone working with the data later? And then the last question is, how much computation time can you afford? Because we will get to that in a second, but privacy is another requirement that you add to your model training. And requirements usually don't come for free. So privacy, for example, costs a lot of computation time. So before you decide for a method, it's actually really important that you know that you will have all the resources to do so. And given on those questions, once that you have the answers to how your setting will look like, you can choose from any of the following methods, which are homomorphic encryption, federated learning, secure multi-party computation, and differential privacy. And in homomorphic encryption, you have basically the setting, you have private data, but you might not have all the resources to train them. For example, you have a lot of image data, training large machine learning models on them costs a lot of GPU power. You don't have that, so you need to do it on a server of someone else. But of course, the moment that you shift your data somewhere, your data is really vulnerable in transit, on the server, and also on the way back if you go there to get your results. So the question is, what can you do here? And the answer is homomorphic encryption. So what you will do is to kind of encapsulate the data with you. And before sending the data out, you will encrypt it and then send it to the server. And then at the server, some computations take place. It will get sent back to your local machine, you decrypt it, and you get the result. But of course, this is a really interesting question because encrypted data, if you have maybe followed a cryptography course, encrypted data should just look like random bit strings. So there should not be any information of the data available in this encrypted data. And therefore, you need homomorphic encryption, because homomorphic encryption is a way how you can compute computations on encrypted data. And if you decrypt it, the result will actually be exactly the same as if you had computed the same things on the non-encrypted data. So your result will, so to say, be correct. And of course, that takes away all the struggle. You're good on transit, you're good on the server, and you're good on the way back. But homomorphic encryption comes at a lot of costs. So especially if you want to learn really complex functions like a neural network, you will need a lot more computation time to do so than if you do it on the unencrypted data. Another setting that you could imagine is that you are distributed. So for example, you're a company and you distribute smartphones. And like, for example, Apple does that. They have they want to learn something from their users. For example, what words they type in, they want to learn the custom dictionaries. So you have a lot of data generated on the user's devices. And of course, what you would like to do is to collect all of that in one central model. One way you could do that is to take all the data from the user devices, shift it to you, and have a trusted environment, and then execute all the computation, and you're good. But there might be two issues with them. The first one being your users might not be super happy if you shift their entire, for example, WhatsApp communications to your server. The second one is, especially in mobile devices, you never know, for example, if your customers are not using Wi-Fi at the moment, you would need to use their mobile data to shift extremely large amounts of data, and the customers might not be super happy about that. So what would be better is if the user data could stay on the user's devices for privacy and also for communication overhead. Therefore, you start with an initial model that you train locally on some data that you have from some users, and then you redistribute that model to all the client devices. And on all client devices, the models are trained locally with the data that the users have there. And then instead of sending the entire model and sending the entire data back, you just look how has the user data changed the model, and how would we need to change the model parameters, how would we need to update them, and then you send this weight or parameter updates back to your original model, you execute them all on your original model, and you're good. Of course, sometimes these weight updates, these model parameter updates, they might also be privacy disclosing that because they hint to a very specific direction. So what you can do in this case is that you just put some noise on them. So you don't have the original weights, but you have some noisy weights where you cannot entirely see what they point to. But by having so many different noisy weights, they will average out if you just put them on your model and execute the updates, and you're super good to go, and you can just do this process again and again, keep on training your model, and then sending the new version back to your customers and then getting it back, etc. So this is very comfortable. Another field which is really inspired by cryptography, similar of course as homomorphic encryption, is the so-called secure multi-party computing. And in secure multi-party computing, you're in a setting where you have different parties. For example, different hospitals that all have some kind of private data, and they want to compute a joint model on it, for example, to predict an illness or so. And of course, these institutions are not allowed to share their data with each other. So what they can do instead is to use this secure multi-party computation in order to exchange some secrets about their data. And that sounds really abstract now because it's a really complicated concept. But you can just imagine they share partial knowledge about their data that does not allow anyone else to reconstruct their data. And with these partial knowledges and secret shares over all of them, they communicate and compute a secret function. And they just approximate, for example, the neural network or the model. And secure multi-party computation is actually really closely related to homomorphic encryption. Both stem from cryptography, but they have one difference. In homomorphic encryption, you need a lot of computation power, as I already said. And for all the secret sharing in secure multi-party communication, you need to do a lot of communication between all the different parties. So one adds an overhead in computation time, one adds an overhead in communication time. And basically right now, communication might be cheaper than computation. So some settings might be preferable to use secure multi-party computation. But again, it's very, very dependent on the use case. But now let's talk about a use case where basically everything is like it usually is in machine learning. If you look in a really standard setting, you have your data with yourself, you're allowed to access it, all the ones in your team are allowed to access it, but you're afraid that someone from the outside will learn something when they can analyze your data or when they can have access to your machine learning models. And this is where differential privacy comes into play. First of all, it might not be super intuitive that if someone does not have direct access to your data, but only has access through some analysis, for example, a machine learning model, that this might actually be privacy disclosing. But let me give you a little example that shows that already on a really low level, these data analysis can violate privacy. Imagine you have a data set with several individuals, and you want to provide to an outsider, to a potential attacker, the average height of these individuals. So you collect all the individual heights, you're good there, the table stays with you, but then the results, so the mean of the heights of the individuals goes to an outsider. And you might say, so far so good, this mean does not say anything about any individual. But now imagine that we include another individual into this data set. And as you can already see, this individual is much taller than the other ones. So comes with a stunning 1.95 m. And of course, then it would change the average value from 1.72 m to 1.76 m. So what that basically means that if someone has both of these mean values before adding the individual and after adding the individual, this attacker will be able to learn that the person that you've added is actually really, really tall. And this discloses this person's privacy. So what we can do here is to add noise somehow to dissimulate kind of these relationships. And the first part where we could add the noise would be on the data itself. So instead of reporting or keeping our table with all the real data, we just put some noise, for example, from a Gaussian or Laplace distribution that look like this, if you're interested, on the data. Then the values would kind of look like this, all a bit more similar. and the mean values would change such that maybe you only have 1.74 meters in comparison to 1.75 meters. And of course, as everyone knows that there are noisy results, this might also be just a result from adding noise, and the privacy of the individual would be more or less protected. But sometimes if you see already, if you need to add noise, then you might have to alter the data a lot. And if you want to add this data, or if you want to use this data for a later computation, the noise might just destroy some correlations or some important information. So what would actually be better is if you don't put the noise on the data, but instead you put the noise on the algorithm somehow. So how would that work? Let's go back to our original data. And we have these two very different mean values. And then you put some noise on these mean values before you report them. So you create a noisy mean function from your original mean function. And then, of course, you can see I cheated a bit here and took very particular noise, but the data might look like pretty similar like this. And the privacy of the individual might be or will be protected. This, of course, brings us to some questions, which are, how much noise do we need? So these different curves, the normal distribution or the Gauss distribution, Laplace distribution, they all have different shapes. So from what shape will we actually draw the noise? So what will we add to the data, to the result in any way? And whose privacy do we want to protect? So right now, with this noise that we added, we are able to protect the individual of the privacy of this orange individual. But imagine now that we have a pink individual, for example, that joins the data set, and this pink individual is like really, really tiny and just measures 1 meter. So again, the results of the mean values will be changed a lot. And the amount that you choose of noise in order to protect the orange individual might not be enough or might not be good enough, large enough to protect also the privacy of the pink one. And then the next question is, how much privacy do we actually need? So will it be enough if one result is 1.75 meters against the other result being 1.74 meters? Or do we need the values to be exactly the same? So how close do we push the results? And luckily, to all of these questions, differential privacy provides the answer. And I try to make it much intuitive for you in the beginning by formulating out the theoretical idea that we will see in the equation soon. But differential privacy basically states, in order to protect privacy of an individual, the results of performing an analysis on one data set without that individual should be roughly the same as on another data set with that individual, but otherwise just exactly the same as the first data set. And how this would look like in a formula, before you get scared, let me explain. We state in the randomized algorithm M, which will be in our case the noisy average, we will have epsilon differential privacy if for all neighboring data sets, and D1 will be the data set with only the green individuals, and D2 will be the database with the green individuals, and then potentially any other individual, like a pink one, an orange one, a violet one, can be anything. And given an element of the image of M, so an average height that can be produced by the algorithm, so can be anything from, I don't know, 80 centimeters to 3 meters if we look at realistic heights, then the formula says that the probability, if we execute this noisy mean on the one data set, the probability of obtaining a specific height value S should be more or less the same as the probability of obtaining the same result on the other data set. And this thing, more or less the same, is expressed by the e to the power of epsilon equation part, and with epsilon being the privacy parameter. And maybe by seeing on the formula, you will already get a feeling. If you input a very, very small value for epsilon here, then the term e to the power of epsilon will be a small value as well, such that you only allow the probabilities to differ really, really marginally. And this means that you protect the privacy really well because the values will be really, really close. So in a setting with a small epsilon, you have good privacy. And on the other hand, A large epsilon will result in e to the power of epsilon being really large. So you allow the probabilities to differ a lot one from the other, and thereby you have much fewer privacy. So big epsilon is lower privacy. And you might also have a relaxed formulation of epsilon differential privacy with the term delta. That is just a term that you could add here on the one side, and it would basically allow you to violate this equation in delta many cases. And now that we have this formulation of differential privacy, we have questions again, namely, where would we add the noise? Would it be the training data? But I've already talked about the fact that adding noise to data might not always result in ideal analysis, because you might break correlations, you might alter the data too much. So one might rather add this noise on the prediction output, but then you run into the problem that your model still stays unprotected somehow, because you would have the private training data, you would have the model, and then just on top of the model as an extra add-on, you add your privacy by just altering the model predictions. And then again, if someone can bypass this external module, this person will still have access to your private model. So this might not be an ideal solution anyways. So a solution that you could do is to add the noise inside the training procedure, so to the training process. And this is basically how the concept of differential private machine learning came up. And I would like to introduce to you two different algorithms that you can use in order to perform this kind of noise adding during a machine learning training process. The first algorithm that I would like to talk about is the so-called differential private stochastic gradient descent. And in this setting, we use a normal stochastic gradient descent, which is just how machine learning, this is actually the process that I explained to you of always updating the model parameters according to the weights, and we make it private. So let's have a look on how such a normal stochastic gradient descent would look like. We would just start with our training data. Then we would formulate a loss function, so a function that allows us to measure how much do our predictions differ from the original labels. We would have the model with its parameters. We would have a number of epochs. So basically this specifies how long will we train. And we will be given a so-called learning rate. This learning rate just reflects from every update when we change the model parameters, will we change them largely or just slightly? And given all of that, what you would do is you take a batch, so several samples out of your training data, and you forward them to the model to get their labels, and you compare them with the original labels, and you end up having the loss. And based on the loss, you now need to alter the model parameters, and this is basically where the gradient descent takes place. So the gradient shows into the direction for every model parameter how you would need to update it in order to minimize the loss. And exactly this gradient telling you how much the weight should be changed and to what directions. And now if you know how much you should change this, you basically can apply it to the model and do the updates. And here I left step 4 and 5 open because you will see that this is where the privacy will come in. But actually then what you do at the end is to update the weights according to your gradient and according to your learning rate. And then at the end, if you have done this as long as you have specified by your epochs, then you will end up with a trained model. Not super difficult. And the good thing is that also training that with privacy is also not that difficult, but maybe not that intuitive. But imagine now you want to add privacy to your learning process. What you will need, first of all, is 2 more parameters. The first one being a noise level. So we've seen differential privacy always works with noise. So in order to let things not be deterministic, we add random noise to dissimulate some connections. And in this case, we also need a clip value, and you will see what we need that for. Because we'll proceed exactly the same. We will take a batch of samples, compute their loss, compute the gradients, and then we will change the procedure here. So not for the entire batch in the best case, but for each individual sample, we would look at the gradients that this sample has. And the first thing we would do is to clip them. why would we clip some values in a gradient? This is because in our setup, each training data point contributes something to the model. So the model would like to learn something from the training data, and some training data might provide a lot of insight. So the model would learn a lot from this training data point, and some points might just like be average and not make the model learn so much. But exactly these training data points that add so much for the model to be learned, their privacy might be disclosed because they cause a lot of change in the model. So the model exactly wants to fit them and thereby might reflect them too closely. And this is why we define a clip value and say every value that is higher than our clip value will be just clipped to this value, such that we put a top, like we say that no point is allowed to change the model more than the clip value. And once that we have all the gradients in the same range, then we can just add some noise according to the noise level, such that we dissimulate again a bit the influence of every data point. And then on this noisy clip gradient, we do the model update and we return the model. And together with the model, we can also calculate the privacy budget epsilon that we've spent for the training process. And what we then have is a private model, basically. Another way how to do it, and it's an algorithm that might maybe seem more intuitive at the first sight, is the so-called Pate algorithm. And what you do here is that you start with your initial training data and you cut it into slices. So it's disjoint slices of the training data. And on each slide, a different model is trained. These models will be called teacher because they are just there in order to learn something from the training data and then teach this knowledge to someone else. Why is this important? Because now the teacher models have seen the private training data, and we already know if someone has seen my private training data, we could conduct all kinds of attacks on their membership inference, model inversion, attribute inversion. So these teacher models definitely have a privacy risk. But what would be if we had the knowledge, but just on different data? And this is what Pate makes possible by taking some unlabeled auxiliary data. So it should be data that is very similar to your training data, but that you might obtain from an anonymous survey or from Kaggle or from basically any data set that is similar to your data and available outside there. And what you can do then is to find labels for this data set, which kind of counts as a transfer of knowledge. So in order to classify the data points in this auxiliary data set, you ask the teacher what they would think about the label. And each teacher gives their prediction. And based on these predictions, you can calculate a common prediction of all the teachers. And we said always in differential privacy, we need noise in order for things not to be deterministic. In Pate, the noise is added here after the prediction of individual teacher in order to make a noisy aggregate. And then once you have this noisy aggregate, you end up having this original unlabeled data with a label. And this label reflects how the teachers would predict this data point. And with data and the label, what you can do is just that you train another classifier, and we call that the student model because it has learned from the teachers how to treat this data. And the student model has the big advantage that it has never seen your sensitive training data. So what you will do here is that you either throw away or lock them in the Savior teacher models, and then you can just work with the student model and make you have predictions on it. So these are the algorithms. And the good thing is for all of you who want to work with these algorithms, they are implemented already for you. For example, in the TensorFlow privacy library. This is a library that has basically all the algorithms that I talked about so far today, and also the membership inference algorithm. And it takes a lot of work from you, and also does not, or you don't need to care about implementing it correctly, but it's already done there for you. So the first day I started working with TensorFlow privacy, I started what could go wrong, and I'll just do it. Let's have a look. And I took the famous MNIST data set again. I trained a not really tuned baseline model on it. MNIST is a really easy to classify data set. So here for you, I plotted the accuracy of my trials. The blue line is the accuracy that I had on my training data. The orange line is the accuracy that I had on my test data, on the validation data. And you see basically on my test data, I nearly reach an accuracy of 100%. So the labels that I predict on the training data, they are nearly all the time the same as the original labels. And similarly good for the unseen validation data somehow. And then I thought, okay, now let's use privacy. And I started looking and searching for parameters that I could use. And I ended up training a differential private model with an epsilon value of 0.45, with a noise value of 5 and a clip norm of 1.5. And you see that the results are catastrophic. Like depending on the size of your screen, you might even see how catastrophic they are, because the two images we have here, they're not even on the same scale. So whereas the first picture gives an accuracy up to 1, so 100% correct, this other picture here just goes up to 75% accuracy. And you see we have 75% accuracy, and then we get worse and worse and worse. So I looked at this and I was quite devastated, and I thought, oh well, maybe differential privacy is just not working out. And then I started reading a bit more into it, and I started looking a bit deeper in these parameters. And I thought I really want to have a low value of epsilon. So what could I do in order to have a really good private training? And it turned out I could keep the same low value for epsilon, so good privacy, if I just keep the same amount of noise, but I clip at the different threshold. So here you see I am reaching a bit over 90% of accuracy on both the training and the validation data, which is not as good as the original model, but not as catastrophic as the other one. Given that the training with differential privacy in these libraries uses much more computation time than the normal training, because in the normal training, you're always considering batches of data. But here in differential privacy, we saw in the differential private stochastic gradient descent that we look at each sample individually, and then we clip it, and then we add noise, and then we do the update. So this takes a much more computation time, and things that you would do in normal models usually, they just take a much longer. So for example, in normal models, you would run some hyperparameter tunings to find a perfect model that fits your data. And you could also use that to find a perfect noise multiplier and to find a perfect clip norm. But as training of any individual differential private model takes a long, long time, it's way time consuming to do hyperparameter tuning. So it's much more, in my opinion, much more difficult to end up with a set of parameters that bring a good model. But in any ways, we're nearly at the end here. I just wanted to show you the picture in order to give you some little takeaways, at least that I took from my work with this. And the first takeaway is any tool's effectiveness just depends on the correct use. So if someone asks you, is differential privacy suited for machine learning? You can say again, that depends. You saw my first devastating results, after which I was questioning, is it suited in any ways? But yes, it turns out I could achieve much better results if I use the tool correctly and if I put in the correct or better parameters. The second takeaway that I would like to give you after today's lecture comes back now from the end of the lecture to the beginning. And it basically refers again to the Netflix example, where we had a privacy leak just because of misconception. Because the researchers at Netflix, before publishing the data anonymously, really thought they were doing a good job by replacing the user IDs and the movie IDs by integer IDs, such that they thought it would not be able to find out again. So I don't think that they wanted to harm someone, but they had just this misconception that replacing the original name by an ID would be good enough. So whatever you do, especially in machine learning, where you might not entirely understand what is going on in the models, if you don't have the right conception of what's going on, you're always risking to to get some problems here and to lose privacy because you just didn't know any better. What we also saw is, as well in the Netflix data set, as well as for machine learning, there are methods to preserve privacy. But of course, they won't come for free. So sometimes you might add a computation overhead, for example, this with the differential private models or the homomorphic encryption models. This might also be an overhead in terms of understandability. So if you want to sell your model to someone, it might be already quite hard enough to sell them a machine learning model that's doing this and that job. But imagine having to explain them the whole story of differential privacy and of privacy in total. So this is an overhead that you shouldn't underestimate if you want people to use all these methods. And the last thing, and this is a thing that's very personal and that I find really important and that especially reflects in privacy, is that you should definitely communicate and you should exchange your ideas and encourage interdisciplinarity. Because what we saw here, many of the methods, homomorphic encryption, secure multi-party computation, all differential privacy, they are all inspired by cryptography. So isn't it actually great that you can take machine learning and you can take methods from a whole different subject, and if you apply them together, you will end up with secure and private machine learning. And this is basically how all the things keep evolving. If you just ask people about what they would think about privacy, what is privacy, what different levels of privacy exist, then you might end up at the end with models that cover a lot more parts of the term of privacy, for example, as well. And I think this is something that we should aim for. And this is basically where the lecture of today ends. And I'm really looking forward to the discussion with you.